Thank you very much. So the basic question that I want to talk about today in this paper is how do we think about the degree of goodness of fit of data for various types of decision theoretic type models that we use to microfound our sort of more complex systems in economics and computer science. Now, any kind of decision theoretic model, be this assumption of quasi-linearity, expected utility, expected discounting, these only describe behavior necessarily in a very stylized fashion. Reality is high dimensional. And as an immediate and trivial consequence of this, though, we shouldn't expect that any sufficiently rich data set is going to be exactly consistent with any of these models. By definition, they're throwing away lots of information, they're describing behavior in a stylized way. And as a consequence of this, what we really should be interested in are how do we quantify the shades of gray? How close is the data to being consistent in an appropriate sense, and what makes for an appropriate sense of measuring proximity to consistency? And lots of your old-fashioned revealed preference type indices that are GAR or congruent to say the data is consistent, yes, not consistent, no. These are good, but these are a first step. And what we should really be interested in are these sort of shades of gray in between consistency and inconsistency. Now, classically, the way this exercise has been carried out, I was interested, let's say, for sake of conversation and figuring out how well approximated the subject's preference is by, say, Cobb-Douglas utility function. What I might have done would be go out, gather some price and consumption data, scanner data perhaps, and I would try and measure, say, the mean squared error between the predicted and observed demands as I vary the sort of choice of fitting Cobb-Douglas parameter. Now, in 1990, Hal Varian came along, and he argued that this approach, trying to use these sort of statistical notions of loss applied to choice data on the consumption space, was quantifying what he termed as statistical, rather than economic content of these deviations. And he argued that these were essentially, could be arbitrarily unrelated to each other. And what he pushed for instead was the use of more micro-founded, more sort of revealed preference type inconsistence indices that have more compelling behavioral interpretations than just say mean squared error between demands. And he argued that what these were doing, these would let us actually talk about, in a more meaningful behavioral sense, how well a theory is reflecting the choice behavior of a given agent. And it turns out that there's actually something to this critique. There's a gorgeous paper by Yoram Halaby and his co-authors in the JPE in 2018 that actually did the experiment and said, what if we calibrate some decision theoretic models using revealed preference indices and look at how well they predict that sample? And what if we calibrate some models using mean squared error between predicted and observed demands, and then see how well those predict? And you actually end up predicting statistically significantly better out of sample when you follow the variant of same. So there's something to this. But unfortunately, this immediately takes you to a kind of tension. There's this fundamental trade-off between the approaches. Variant calls for more economically meaningful, revealed preference type indices, but these really carry with them a whole host of different downsides that are really pretty inescapable. Almost every revealed preference index we look at, they're seemingly a little more behavioral, but really they often get attributed a lot more sort of economic meaning than they warrant. Federico Angeliche has a great recent paper addressing this. There is an entire cottage industry of NP-hardness results for all of these things. Almost every sort of classical revealed preference index is NP hard to compute. It's all these very difficult combinatorial problems. And because of this, it's also really unclear how to sort of introduce things like error or noise or stochasticity into these models. If I have some revealed preference index and I want to get a distribution to construct hypothesis testing under some hypothesis of noise, what I was going to do is calculate a bunch of different times and different types of noise, but I can barely calculate these things one time. So they really don't seem like a natural place in trying to develop a more modern econometric type theory for these types of models on the basis. So for today, I want to talk about a almost completely different approach to measuring goodness of fit. And the idea is fundamentally going to be, can we solve a data engineering exercise that's going to let us get richer, more nuanced, in particular cardinal data, which we can then use to construct the types of tests we want to in a tractable and economically meaningful way. So just because it's going to be a short talk, let's do a worked example. Suppose that we have subject whose preferences are just over bundles of two commodities, money and apples, let's say. And our goal here, we want to measure how well the subject's preference is going to be approximated by some continuous and quasi-linear utility. Here, quasi-linear is quasi-linear in mind. So to get at this, we propose running the simplest possible experiment that you could probably all think of yourselves. What we're going to do, we're going to take three different bundles, bundle 1, 2, and 3 of just money and apples, and we're going to assume they lie in general position. And now for every pair of bundles, every pair of pairs, we're going to assume that we observe from the subject two different things. And this could all be elicited in a dominant strategy out of the way, but just for today, let's assume that we observe two pieces of information. First, which bundle in a given pair is preferred to which other bundle. So this is a bog standard revealed preference observation on a binary choice set. But in addition, we're also going to assume that we observe how much extra money, how much extra numeric good will be needed in addition to giving the subject the less preferred bundle in a given pair in order to make them indifferent with receiving the more preferred bundle. So if they like bundle I more than bundle J, fine, we observe that. But we also observe this non-negative quantity alpha Ji, which solves this kind of orbital equation and makes them indifferent between bundle I and the augmented bundle J. So you can think of this as we're trying to figure out how much extra money the subject would be willing to pay in order to switch bundle I and bundle J. So willingness to pay observation. And we're going to turn this alpha Ji, the compensation difference from J to I. So maybe this is what these bundles look like in practice. And we observe that bundle 2 is preferred to bundle 1 by some amount alpha 2, 1. So geometrically, all this means is that if we take bundle 1, we translate it to the right by alpha 2, 1. It's going to lie in the same indifference curve as bundle 2. And maybe we observe that bundle 3 is preferred to bundle 2 by some quantity alpha 2, 3, the same type of intuition. But now, I claim we're actually in a position to obtain testable implications of quasi-linearity. Because if the subject does have a quasi-linear preference, then all of these indifferent surfaces have to be horizontal translations. And what that means is that the subject must like bundle 3 if they're going to be consistent with quasi-linear preference. They must like bundle 3 more than bundle 1. And in fact, the compensation difference from 1 to 3 has got to be equal precisely to the sum of the other two compensation differences. So taking stock, we have an experiment where, unlike choice data, where I had, I observed that X was chosen in the presence of Y is revealed preferred. Here, the data set isn't a sort of directed graph or combinatorial object, it's just a vector. The vectors alpha 1, 2, alpha 2, 3, alpha 1, 3 tell me everything I need to know about the data. If say alpha 1, 2 was negative, then I know that 1 was preferred to 2. If it's positive, I know 2 is preferred to 1, and these give me the magnitudes. So here, we have an experiment where the set of all possible data sets is just going to be R3. And we've said that as a necessary condition for quasi-linear rationalizability, the data has to satisfy the single linear adding up equation, essentially. It's not too hard to show that, in fact, this adding up condition is actually also sufficient. Every data set satisfying alpha 1, 2 plus alpha 2, 3 equals alpha 1, 3 actually arises as the compensation differences of a continuous quasi-linear preference in our consumption space. And so now, rather than a condition like GARP or something like this, where we have lots of different inequalities to check, we have a really simple condition. The data are consistent with a continuous quasi-linear preference if and only if they lie in a given plane in R3. And in fact, more can be said. So let's suppose, just for the sake of conversation, that the data we observe is alpha 1, 2 is 3, alpha 2, 3 is 4, alpha 1, 3 is 1. This is a quasi-linear rationalized. It doesn't satisfy our added condition. But we can decompose this data additively into two other vectors, 1, 2, 3, and 2, 2, minus 2. One way I like to sort of attribute a bit of a visual of what these data vectors are saying is imagine we represent our experiment by an undirected graph. I'm going to have one vertex for each of these bundles, each of these three bundles, and I have an edge connecting any two vertices that we're going to elicit this compensation differences between. So here we get it for every pair, so the graph representing our experiment is going to be the complete graph on 3 vertices. I can think of any data set then as defining a flow on this graph. So all I've done here are just write 3 sort of graphical representations to these vectors. Now this decomposition was carefully chosen. 1, 2, 3 does satisfy our condition, which means that it is consistent with some quasi-linear preference. And now 2, 2 minus 2, when we look at this as a flow, this is a cyclic flow. Inflow equals outflow at every node. So economically speaking, you can think of this as being like a money pump opportunity against the subject. If you're willing to trade bundle 1 plus $2 for bundle 2, bundle 2 plus $2 for bundle 3, all the way around a circle. They can be played for a money pump by a savvy arbitrage. So this is like cyclic inconsistency or cardinal sort of revealed preference cycle. But note as well that just as a vector, 2, 2 minus 2, not only is it going to be orthogonal to anything, or 1, 2, 3, it's also going to be orthogonal to anything which satisfies our adding-on conditions. And so as a consequence of this, 1, 2, 3 is actually going to be the orthogonal projection of our inconsistent data onto the rationalizable subspace. And what we find here is a general phenomenon. When we project least squares, our inconsistent data onto the quasi-linear rationalizable plane, we're going to get a residual, which is just a revealed preference. And so this suggests a least squares type methodology for measuring consistency and trying to calibrate models and so on and so forth. If our data are not rationalizable, there exists a unique mean squared error minimizing rationalizable vector compensation difference, just given by orthogonally projected the quasi-linear rationalizable problem. By minimizing mean squared error, we guarantee that we're purifying away only this cyclic inconsistency, and we're leaving all of the rationalizable material behind completely untouched. The minimizer, the argument from this projection, from this least squares problem, yields a set of restrictions. The restriction which characterizes the set here because we have an infinite dimensional model with continuous quasi-linear preferences that best fit the finite data. And the mean squared error itself equals the minimal quadratically weighted utility loss suffered by any quasi-linear agent were they to accept the sequence of trades that we observed in the data. So this actually has a utility loss interpretation, which is different than anything we can get with the traditional revealed preference toolkit. And this generates fundamentally new insights because it could well be the case that, the expected utility hypothesis, a lay, elsewhere, we see lots of ordinal violations in the lab of the conditions of this theorem. But what this tells us is, in principle, it could be the case that when we see lots of ordinal violations, the total utility loss accruing to these violations could in principle be very small. And if that were true, it would still potentially be quite normatively reasonable to accept these models as a good proxy for behavior if they're tractable and have other desiderata. And this gives us a way of evaluating not only how often do we see the sort of axioms violating importantly, but what is the actual loss under the null of consistency to a subject who generates the predicted data. And this gives us a cardinal measure of the degree of inconsistency. Now, oftentimes, we want more than just quasi-linearity. Maybe we want a richer model where I want to consider only those preferences that are quasi-linear, continuous, and increasing, and convex. This is sort of classic demand theory type axiom. Well, if we layer on these additional assumptions, it's not hard to show that the subset of data vectors consistent with this more structured model just now form a polytope instead of a linear subspace. So what have I done? If I want to do mean squared error minimization, now I solve the least squares problem subject to some finite set of linear inequality constraints rather than just an unconstrained problem. It turns out it's very tractable to write down what these inequalities are. And in fact, this estimation procedure actually still has some nice properties, even in this sort of more structured world. In fact, the mean squared error will now decompose additively in a unique way as the sum of the squared utility losses due to these money pump-like behaviors that we saw in the pure quasi-linear case. And then as a separate additive term of what are the utility losses that accrue due to violations of the other model axioms. And what we can also do is do the same exercise for sort of intermediate models, where it's quasi-linear and just increase, quasi-linear and just convex. And we can look at how much more utility a consistent subject would have to lose to explain the data in each of these individual intermediate models and get a kind of shadow price in model fit terms of how well or poorly supported individual axioms are in the data. Now, quasi-linearity is very special, it's very simple, and it's sort of great, having numeraire good, you can imagine that this would work, but it's not at all clear a priori how this works for actually the kind of models that we really want to look at more generally. So what the paper does is it introduces a concept of actually a virtual commodity. So here I now, let's suppose we're in full generality, I have a general abstract metric consumption space X. A virtual commodity is just going to be a family of maps, each taking X to X, indexed by some non-linear number. And the interpretation I want to fix to these transformations is that phi subscript alpha of X represents the ultimate of X plus alpha units of extra commodity. And now these axioms just ensure that this is sort of a reasonable interpretation of what this is doing. So here in the quasi-linear world, you could have thought of our maps as just being translations along the linear axis, but this is a kind of coordinate-free generalization of the notion of commodity to abstract settings. In the interest of time, I'm going to skip through these very quickly, but I give you a set of axioms which are necessary and sufficient for the following utility representation term. So under the axioms that we just passed very quickly, a preference, those are necessary and sufficient for a preference to admit a utility function that satisfies the following infinite system of functional equations. Whenever I look at the utility of any x plus alpha units of this virtual commodity, that equals the utility of x plus alpha. So what this is just saying is that if you give me a virtual commodity that satisfies a certain set of axioms that are in the paper, it acts like a numeraire good, just the way that money would do for a quasi-linear person. And this, in fact, can be done in completely abstract consumptions. We're no longer tied to having a literal x-axis in our consumption space. You can give me an abstract metric space, and we can make sense of now what a numeraire good is. And what this does is it gives us a means of identifying observable willingness to pay measurements denoted in an appropriate virtual commodity with unobservable utility measurements, just the same way that money let us do this in the quasi-linear world. And this can be done in lots of different contexts. So, for example, if you're interested in Douglas preferences of a model, I can instead choose a virtual commodity, not translation along one of the axes, but rather scaling along range of the origin. And this can be shown to essentially act the same way a numeraire does in the quasi-linear world. This can be done for expected utility. Not going to get into the details just because of time. In fact, it can be done for pretty much every type of domain and every type of decision theoretic model that we're interested in economics more generally. And the takeaway from this is that we can do compensation differences using virtual commodities. I say, okay, in the Douglas world, we'll allow virtual numeraire scale bundles. I say, here's two bundles. How much do I have to proportionally scale up the less preferred bundle to make you a difference with the more preferred bundle, for example? And when we get willingness to pay data, compensation differences in a virtual commodity, all of the results that we saw in the quasi-linear world remain true in full generality. These set of data sets that are for an arbitrary experiment of this form that are consistent with some scare quotes phi quasi-linear utility, satisfying a narrow characterized by an analogous linear system of adding up conditions. The orthogonal complement of this subspace precisely consists of sums of cardinal revealed preference cycles. Almost all the time, individual models will form polytopes. And when we project onto polytopes in this space, we're going to get this additive decomposition of the mean squared error, which will have a utility interpretation as sums of squared utility losses due to sort of money pump type violations once again, and to losses due to the data not satisfying other various kinds of model-specific shape constraints. And I am officially probably 30 seconds over. So with that, I hope I piqued your curiosity and thank you.